stream going and the recording going. Just so you know that these presentations are recorded, and you'll have an option to access those later. We have another Samantha for this block. It's Samantha Welch. Samantha, or Sam, currently works as an AM design engineer at the Additive Design and Manufacturing Center at Lockheed Martin Space in Sunnyvale, California. She supports design for aerospace applications and AM process development and teaches a design for additive course. Sam has been working with 3D printing since 2011 and started with building a MakerBot cupcake. I have a soft spot in my heart for the cupcakes while on an internship at the Gulfstream Aerospace, and has worked on countless printers since. She's designed popular items such as Plantigon and modular stacking 3D printed planter. I'm pretty sure I have printed one of those, which has been downloaded over 250,000 times. Yikes, that's a lot. That's awesome. And printed by hundreds. After graduating from Purdue University with a computer graphics technology degree, she's moved to California to work with rapid prototyping and CAD design at Tesla Motors and Apple, and has recently completed a master's in additive manufacturing and design from Penn State. Through her whole career, Sam has been a 3D printing evangelist who has worked to find useful applications for 3D printing within her work. Sam specializes in design for additive, advanced CAD and generative design, additive training and education, additive process development, and support structure development for laser powder bed fusion. And her talk today is titled Breaking Away the Challenges of Metal Additive Support Structures. Sam, I will leave the floor to you.
Thank you. All right, thank you everyone. I'm so pleased you could join me today. Let me get my screen sharing going. All right, is that working? Perfect. All right, so as mentioned, I recently completed my master's degree from Penn State in their additive manufacturing and design program. And the work I'm sharing with you today is the results and findings from my study for my master's project. So if you've worked in metal additive and if you've worked with supports, you know that they're kind of a huge pain compared to if you're used to coming from the polymer space, like I was at first a couple of years ago before I started at Lockheed. I was used to support settings being a checkbox, supports on or off. I was really disappointed to find out that this was not the case, especially for laser powder bed fusion. Supports were something that needed to be carefully considered, manually applied, and even then had, at the time the settings we're using had, risk of leaving some real ugly marks on your parts. And so with what I was used to from the polymer space, I thought, there has to be better solutions. We're not solving drastically different problems here. And so throughout the years, I've iterated on a couple different settings and approaches and techniques to give us some more robust, easily removable support structures that we use pretty readily on our applications. So I'll talk about some of the background behind how the supports for metal additive are different from considerations for polymers and other additive processes. A little bit more breakdown of the actual geometry of the ones we use most commonly for our metal supports, and then some of the overview of findings from my study. So if you're used to any additive process, it's built up layer by layer, and you need something when you're building a larger feature on top of a smaller feature that results in an overhang condition. If you have a process like binder jet or selective laser sintering, you're lucky and you don't need to necessarily consider that because that powder is going to part. This is not the case, even though this is still a powder bed process for metal, because there's a huge amount of energy differential going on. When we have this really small area of this small overhanging feature, we're dumping somewhere anywhere between 400 and 800 watts of energy into this 30 to 60 micron little strip of metal. And so as that rapidly cools, it tends to curl up, and if it doesn't have anything to wick away that heat, it can be a crumbly mess. If it's not attached to anything, that recoder will come on by and carry your feature away, which doesn't bode well for the layers. If you have a feature that's building up in one direction, as seen in this picture here, depending on how shallow that angle is, it can really deteriorate quite significantly. And across industry, it's still a huge point of variability, such that the design for additive rules generally recommend, if you don't need supports, don't use them, design them out whenever possible. And this is because a lot of places, don't necessarily have the time, resources, or someone is interested in this otherwise throwaway part of the process to dive in and optimize those. And so part of the goals of this is to give people a better framework to start from, that if you're struggling with supports now, here's some settings you can use, and hopefully go from there to find something that works good for your application. But there's a huge amount of variability available just because of the wide variety of parts that we're often printing for this process. So as I said, for metal, they're really functioning quite different. They're not necessarily providing kind of a gravity feedback like they are for polymers, but they're really more of a anchoring to the build plate, thermal interface. And as we're looking at different alloys as well, like each of those have different thermal conductivity. And so the way that these are functioning is also going to change. And so that kind of changes the different factors at play when we're applying these, and also when we're considering how to design and also how to set up a build. So this is some level of a shorter term issue. We've got, on one hand, you can develop better supports and better designs, but then on the other hand, there's process control improvements that are in works, such as selective parameter modification, things like downskin, upskin modifications, and then, full process modifications to the extent like what Velo 3D does. However, this makes it so we need to use a lot less of the supports, but there's still going to be times when they're going to need to be in place. There's going to be some level of them that I think will be unavoidable for the most part. So as someone who's setting up builds, often you're in a place where you need to decide, okay, where are supports needed, what type to use, is the part supported enough? If I put too many supports on there, I'm driving up my post-processing time. I'm adding, potentially costly post-machining steps, or even just more labor to file and break these away. However, if I err on the side of too few supports, now I'm risking, maybe some deterioration in my part geometry, or at worst, a build failure. So when we're talking about parts on the level of, maybe the size of a baseball, where it's a day and a two to build, you've got a little bit more room to kind of optimize. And if you need to rerun it, maybe it'll take another day or two. As we're scaling up into these really large platforms, like Dexline that I'm used to working with, a large build on there can take a week or two. And so I don't necessarily have the luxury of being able to iterate when my build is going to take, longer than a week. I need to make sure that it's right. And any modifications I make, if I add a lot of supports, that's driving up the build time even further. So as additive scales further into these larger applications, into higher production runs, optimizing this becomes ever more critical. So the most common support structure that we use is these block supports. I chose to focus on these because they're pretty widely available. There's a number of other, approaches to this, and some fairly costly software solutions that not everyone has access to. So given, the things I had learned in the polymer space, I thought there had to be some transferable part of this to the metal additive space, given that there's plenty of different geometry options to play with to get something that I could break away with pliers or air file rather than needing to break out, a mill. So the critical parameters involved here, and when I say parameters, I'm referring to geometry variables, not necessarily part parameters, laser parameters, is going to be that part to support interface. That's what all of this tends to come down to, is that actually where my support is attached to the part. And commonly it has this kind of tooth interface. The tooth height is one parameter, the tooth contact width is another, and then there was this other function, Z offset, which is how much it's kind of set into the part. And based on the research we'd done and some of the studies I'd read, we weren't quite sure how that influenced things. We knew that it did, and I wanted to characterize how. So I created this study basically to determine, now that I had settings that I was fairly happy with for aluminum, I wanted to know, which knobs to turn to customize them for a certain application, and which things actually were influencing the overall strength of a support structure. And then also, like I said, I'd primarily been working in aluminum up to this point. I wanted to know how transferable this was, titanium 64 or stainless steel. So for this study, I had my kind of baseline settings and then tested a few key variables within that space, as well as having it produced on a fairly wide range of materials and platforms. I asked the operators to use their standard processing conditions. I didn't want to get into a whole parameter study, but I will say that if you're struggling with the supports and them failing on parts that you feel like they should be able to work on, I would look at your part and support parameters first before getting into this side of it. So the coupon I designed for this is a fairly straightforward tensile bar. It had your standard sub-size ASME E8 style. Kind of looks like a guy standing there with his hands on his hips or with your hands in your pocket. So I had a stepped region to better inspect that critical part of support interface. I had these protective arms since some of these are going to be printed at various places around the country, I didn't want the supports to get damaged in printing and affect the results. So I had these arms on there that got snipped away before the tensile pull. So for the aluminum samples, I CT scanned them. If we're going to get tensile data out there, I need to know my cross-sectional area. And it's not quite as simple to measure as it is for a bulk material, and it's this fancy grid pattern. So all the aluminum samples were CT scanned. We had a modified Python script to extract the cross-sectional area as a function of height throughout that part. And then after that data was collected, the tensile pull was performed, as well as a removability evaluation afterwards. So some of the first results that I found quite interesting were from this cross-sectional area. I had assumed that the top interface would be my weaker interface, where the support ends and my part builds. I thought that would be kind of where things were likely to break, but that wasn't what I was seeing. I was seeing my tensile bars were frequently breaking at that lower interface, and this was also reflected in the CT data as well. It was a small difference, but overall consistently they were slightly larger in cross-sectional area at the upper interface than the lower interface. And this actually traces back to a phenomena from the laser process itself. So similar earlier where we talked about how the function of these supports is kind of wick away that thermal energy as it's being dumped in. When we are melting unsintered powder, the melt pools are actually larger because they're spreading more into kind of that neighboring area and not necessarily being wicked away into a solid substrate. So those larger melt pools actually translate to the cross-sectional area of the top of the part being slightly larger consistently, and therefore, because the cross-sectional area is larger, it's not necessarily the weakest point in my tensile bar. Physics still applies no matter how complicated of shapes we're printing, and the bottom of the support is going to be my weaker interface. So that was a good find. It was something good to keep in mind as we're approaching these. The next interesting results I found were of the tooth height. A lot of the papers I was finding, kind of other recommendations, were recommending these, fairly small interface regions, a 0.5 millimeter of tooth sizes. I just really hadn't had luck with those in our applications, and we were using much larger tooth heights. And I had a kind of an inkling as to why that did actually get chased out in the study, and that when you're working on these smaller platforms with smaller laser powers, smaller spot sizes, and therefore smaller melt pools, you're able to resolve these small features repeatably. But as we're scaling up to higher power laser settings and larger platforms, our small features don't quite resolve in the same way unless we're specifically optimizing for that. And so the larger teeth were able to resolve more repeatedly across these various settings and platforms than the smaller teeth, so which gave us kind of a more robust repeatable result, which is what you want when you're printing fairly critical parts. I also found that for the aluminum parts, this correlated with the minor improvement in strength. The larger teeth were easier to remove and were slightly stronger. So overall, I recommend if you're looking at this support interface region, these larger size interfaces tend to be more robust and repeatable than these smaller ones. And this is some of the data. It's funny when you get all these samples, it seems like it's just an endless amount of samples to process. And then you actually look at the data and you're like, well, I wish I had way more samples. So look at the curse of any study. But as you can see, most of the modifications here were not, fairly dramatic as far as their influences on strength. Like I said, these are kind of fine-tuning knobs, other than hatching, which gets back to, of course, if it's denser, we'll have more of a cross-sectional area and our part will be stronger. However, I really don't feel that adding that, tighter hatching for that support grid is necessarily worth the strength improvement, because in the removability trial, it really had quite the negative effect. As we moved that grid spacing tighter, it trapped a lot more powder. It was no longer able to be removed with hand tools. And so if you're in need of a stronger support structure, I would really recommend using more of a hybrid approach of a sparse grid and then some solid posts or thin walls rather than densifying all of your supports and making it a nightmare to post-process. So the next one that I got into that was quite interesting was the Z offset. I had seen some influences and couldn't quite chase to what, and there was actually a number of things going on here. Of course, it always is an additive. So when I noticed when I didn't use any of this Z offset, my part actually on some of my samples, the supports were like barely attached to the bottom. The teeth were already lifting up. And then when I did use this Z offset, the teeth were fully attached. It didn't quite make sense to me given that, I'm dumping a lot of energy in and then exposing a small support projection onto it. But when I looked closer into it, there's actually some relationships between a few other variables that were not being caught initially. So when we're doing these laser exposures, the laser's not actually tracing my part edge. It's tracing, set inside of my part edge because that melt pool offset needs to be set so the edge of my melt pool is going to be at my part edge so my part doesn't come out oversized. So when I slice my part, I've got these closed contours, that offset's applied, it's all good. When I slice my supports, they're all open vectors. There's no way to apply that offset to an open vector. And so they were actually being projected outside of my part lines, which is not what I was intending, and something that was detrimental to the strength of these in the samples where that was present. So there's a fix for this. If you correlate your, if you shrink your supports down to the same extent as that parameter offset, now it's going to line up where you think it will. It's just a very odd processing sequence because it's handled in separate softwares and at separate points in the prep process. So it's an edge case, but if it's one that applies to your process, definitely take a look to see if this could be the root cause of some of your support failures. This was something that we observed in the Magix to concept laser workflow, the Magix to SLM workflow. However, if you're working with like 3D Expert and EOS, they handle these more concurrently, so less of a risk there. But so this is what's happening, with Z offset on a single layer, like 2D level. It gets really quite interesting when we get to it over, multiple layers. So one of the edge cases we were seeing is that, as people often do, we had parts that we wanted to start on an edge and then grow into a part. And so we'd have a kind of a single line of supports attaching it, but we were seeing a lot of weird effects and some detachment there. And this is because that offset, as our part is offset within the melt pool bounds, it actually makes it so those first few layers, there's no exposure attached to it because it's offset smaller than, a value that the melt pool would project. So this actually then pushes my part up a layer. And depending on what that melt pool offset is, that can push up your part, multiple layers. If your support is ending exactly where your part edge is, and your part is starting higher than you think it is, then, that's bad news. That's not really setting you up for success in subsequent layers for having a good, strong attachment of your support and for having that perform as it's supposed to. So this was a particularly interesting find. It's definitely something to look into if this is a sort of application or use case that you see for the for support applications or for these types of part geometries. So some of the overall takeaways of the study is that the findings were that the support structures were consistently weaker at that lower part to support interface due to some of the process influence of the as-built geometry. As far as the data collection, I did find that for aluminum, particularly the A205, showed that these support structures have roughly 40% of the strength compared to bulk material. We're still processing the data on the remainder. And then, as mentioned before, using those larger tooth heights is more repeatable across a broad variety of platforms, which makes your part, more likely to succeed if you're transferring it between different systems. Like I said, you can decrease that hatch space to improve your strength. However, it's really kind of a significant caveat of making it far less removable and trapping quite a lot more powder, which is not something you want to deal with while processing these. I mentioned that Z offset has some really interesting interactions with both the kind of the 2D XY offset and then that subsequent layer offset of parts that needs to be kind of matched and considered to your parameter set. And then one of the other things that was tested was testing different heights, because sometimes we're supporting things 2 millimeters, we're supporting things, 200 millimeters off the plate. There was a slight decrease as the support got taller, but not one that was fairly significant. So these are the settings that I recommend. I'm curious to know, for those of you out there who work in similar areas, whether these are similar to ones that are in use or drastically different, or if you get a chance to try them out, let me know how they work for you. It's meant to be kind of a starting framework, because the ones that when I had first started, we started out with were not quite as robust, and these ones give us a much better platform to literally build the part on. One of the other things I want to note is the Recoder Blade. We've had best results with kind of a wiper blade style Recoder Blade, the soft recoder. Not so much, when I say wiper blade style, it's different from those kind of soft silicone nub ones, which can be easily damaged, leave streaks in your part. And then if you're using a metal Recoder Blade, good luck. Those are fairly unforgiving in this regard. So some of the future work, this is, just kind of scratching the surface of all of the different parameters and considerations involved. And one of the things that was collected as part of this study was the influence of these different supports and then the residual surface finish of the part. We're still kind of optimizing and collecting data to find supports that, have the least impact on net surface finish as is possible, given the process considerations. I also am looking into, different impacts of post-processing heat treatments, solution treatments to make sure, remove your supports either before or after and make recommendations like that. And then there's a huge world of opportunity as far as alternate geometries. Like, I think there's a lot of space for SLA tree-style branch supports, for variable density gradients, for alternate lattice styles entirely. There's a gyroid type shape that we use quite often that I think has a lot of applications in this space. But really, one of the things that this is kind of all gearing towards is to aid in further refinements for feature identification for support generation. That way we can have a generate supports button like we're used to for plastics work as it is for metal, because right now the ones for metal are not quite something you'd want to throw into your machine and run. So I'd like to thank the following groups for helping me complete the study. Lockheed Martin Space, it's been a fantastic place to work. I got to run both of these aluminum samples on the machines there, as well as get CT scanning, technical expertise, etc. And then Lockheed Martin Aeronautics provided the titanium samples. And if you remember last year when there was all those crazy, freezing power outages, that was when they were working to get me these samples. So absolute kudos to them for still managing to help my grad study with all of that going on. And then Exact Metal is this really cool lower cost laser powder bed platform running out of, they're an offshoot from Penn State. They provided the stainless steel samples. And then thanks again to the Penn State AMD program and to Dr. Timothy Simpson for advising on this project. All right, questions, comments?
Awesome, thanks so much, Sam. We have several questions, so we'll just go down the line. The top voted question is, do you have any insight on perforations in the block support?
Yeah, actually, I didn't include that in kind of that final summary, but definitely use them. It's not worth trapping all that powder in there. They had kind of a negligible effect on strength as long as you're keeping that beam width. An option there for those perforations is how large or small you want to make them. As long as you make them, small enough that they're not compromising the integrity of your support. My setting is usually around over 0.5 millimeter. That it's worth it, just so you can easily break them apart and get powder out.
Have you done any work with pins, and what are your thoughts on those?
I am now. They're for titanium, they seem like they might work a bit better, as mentioned before. Aluminum's a little more forgiving because it's so thermally conductive. Titanium less so. So that's why we look more at pins for that. But we're just kind of still starting to optimize those now. We've got, you always have ones you're happy with, but you always in the back of your head think they could be better.
I know pins were easier to remove for me, at least when I'm doing them manually with some needle nibs.
Yeah.
Awesome. How do you think your proposed support structure framework will affect residual stress?
It's a good question. And it's so dependent on part geometry and, build orientation and the type of geometry you're seeing that in. We're still kind of waiting on better characterize that so we can get kind of better read on that, but it's fairly part dependent is really as much as I can say for that. It comes down to part of just evaluating it based on prior judgment and the data you have.
Gotcha. Have you worked with dissolvable metal supports? What's your take on those?
There's some interesting work there. I don't know how much, like I said, we're in aerospace and people are very sensitive to any sort of new processes. And one of the things is that it sensitizes the parts, to deteriorate your support structure. And they want to know, well, is that going to affect my part too? I don't necessarily want my part to be partially dissolved. So we haven't looked too much into that. We'd rather just kind of have ones that we can break away easily. But like things like contactless thermal sinks and stuff are definitely more of the leaning toward sort of applications.
What's your favorite support removal tools and methods?
Air file. I love my air file.
Good to know. What's the best down-facing skin surface finish that you've been able to achieve on a flat overhanging surface parallel to the build plate?
Ooh. So it's relative to how, you mean full parallel? Oh, you'll have to wait. I'll have to crunch the numbers on that. Because the trick I've been having there is determining exactly what I'm measuring, because it's one thing to measure, break off the support, and I've got a lot of like agglomerated powder on there, but if I brush it off, am I polishing it? If I go media blast that, is that really measuring the same thing? But I mean, 300 RA is generally our baseline for where we want things, and so I'm trying to determine how much it's deviating like for or against that.
All right. Have you tested the Xerox Metal 3D printer?
No, not yet.
We've got one. We're still getting up and going. Is there any interest in green laser technology for copper 3D printing at Lockheed where you are located?
Possibly. I don't know how much I can talk to that.
Gotcha. All right. That was the last question. Thank you so much, Sam, for this very interesting talk. I think we all understand the pain of support structures and love that you're working to understand them better. So we appreciate that. And thanks again.
All right. Thank you all.
All right. We're going to step down for just a minute before our next session, which is a panel. So we will be right back.